Okay, this is number 104 with two titration curves on one page right here. And there was some other material that you needed that was on the page before, and I wrote it up here already. So there's a weak acid that's being titrated with KOH on this, and that's that curve. And then there's a strong acid, which is HBr right here, and it's being titrated with this curve right here. They both end up the same because up here all you have is the strong base KOH. Starting down here, all you have is HF, and starting down here, all you have is HBr. They both end up with the same steepest part of the curve right here, which is called the equivalence point. And the equivalence point is where the moles of the acid are equal to the moles of the base. And this turns out that there's just two graphs on one graph here, two different experiments that are going on. And so in letter A, it says label the equivalence point in the graph above. So this would be the equivalence point for the weak acid, strong base. And the strong acid, strong base, middle of the steepest part of the curve would probably be like right there. Calculate the initial volume of the strong, label the point where the pKa of the acid is equal to the pH. So that can only happen with the weak acid right here. And that's halfway to the equivalence point right here. And at this point, you have some HF present, and you have some F minus present. And so this is a buffer solution right here. You can see the pH isn't changing very much. And the middle part is where the pH is equal to the pKa. And so for letter B, there's a lot of chemistry going on right there because you've had this reaction going on. HF is reacting with the KOH, and you're going to make some water, and you're going to make some K plus, and you're going to make some F minus. And this are present in great amounts right here. And since this is a weak acid and this is its conjugate base, these two things come together to make a buffer solution. And when it's a buffer solution, remember the pH is equal to the pKa plus the log of the base over the acid. And if we have an equal amount of F minus and HF, which we do right here at this point, that means this fraction would be a number over a number that are the same, and so we would have the log of 1 at that point, and of course the log of 1 is equal to 0, and so at this point the pH would be equal to the pKa. Some people call this the halfway to the equivalence point. Some people call it like the area of most buffering, but it all means the same thing here in letter B. In letter C, it says calculate the initial volume of strong acid used in the titration. So in the strong acid, strong base one, the equivalence point is right here. And at this point, we have equal moles of acid and moles of base. And what I want to know is how many milliliters of this acid I started with. So in letter C, I can say since moles of acid are equal to moles of base at the equivalence point, I could replace those with molarity times liters from the molarity triangle, because moles are equal to molarity times liters. And I could say that the molarity of the acid times the volume of the acid is equal to the molarity of the base times the volume of base. So if I wanted to know how much volume of acid I had to start with, if I knew the molarity of the acid, the volume and molarity of the base needed to reach the equivalence point, I would know how much volume of acid I had to start with. And so my molarity of my acid, I think it tells me, is 0.2. My volume of acid is what I want to know. My molarity of my base is 0.15 molar. And my volume of my base at the equivalence point is 25 milliliters. So now I could solve this for VA right here, divide by 0.2. And I apologize, I'm going to get my calculator out here really quick so I don't screw this up. 0.15 times 25 divided by 0.2. I hope I did that right. Ends up being the initial volume of the acid was 18.75 milliliters to 4 sig figs. If it was only 3 sig figs, it would just be 18.8 milliliters. But that's letter C. And then letter D, label the point of most buffering. Well, that's this area right here in the weak acid, weak base titration that I talked about before and showed you on the Henderson-Hasselbalch equation. Hope that's helpful.